Okay, so today I wanted to discuss about this concept of Shannon entropy and especially the formula of Shannon entropy. This has always been really amazing to me. So basically, we have a pretty simple formula, but it's extremely powerful. Pretty much all the ideas related to entropy in information theory are extremely important. They have very deep consequences, not only in statistics, but in many fields, especially in machine learning. If you have trained some kind of binary classification model, the simpler one, probably you have used the cross entropy loss function, which is actually pretty related to this idea. So today I wanted to show you how this formula is actually derived because this is the first very interesting thing about this. This is not a definition, right? It's not that Shannon decided one good day that basically this is a good definition for the entropy. This is actually something that you have to prove, right? Following some ideas that we will discuss. And I think that the result is actually pretty elegant, pretty interesting, and pretty easy to follow if you pay attention. So I wanted to record this video just showing you what's the derivation of this formula of Shannon entropy because it's actually pretty fun, at least for the people like me that are kind of nerd. So if you remember, basically, the Shannon entropy is one of the different flavors of entropy across the modern science, right? Entropy, you can find entropy in chemistry, physics, pretty much all the areas of modern science uh, have some kind of concept related to entropy, which is essentially the order in some kind of complex system. So in statistics specifically, the definition of entropy is actually pretty interesting and is related to the concept of probability and uncertainty, right? So the formal definition of Shannon entropy is something like this. You can find different versions if you have some discrete probability distribution like this, or if you have some continuous distribution. But all of those definitions are, of course, are the same. They are equivalent at some point. So essentially, if you have a probability distribution like this, right, which that means that all the numbers sum up to one, then you can compute this quantity, right, which is basically the sum of this, the p I, and the logarithm of that pi, right, and then you sum all of those numbers, and that quantity is the Shannon entropy, right? There are a lot of videos in internet, in YouTube, a lot of blogs explaining what's the rationale behind the Shannon entropy, what's the intuition behind the Shannon entropy. So I'm not gonna dig deeper on that. I am more interested in the mathematical part of this result, and that's what I want to show you. But essentially, right? So the central idea of this number is we want to compute some kind of number that basically answers this question, right? How much information do we have given a probability distribution, right? Right? A probability distribution basically tells you all the probabilities that some event in some probability space basically happens, right? So you have some numbers 0 0.1, 0 0.2, 0 0.3. Basically, the idea is how much information. There are some definitions that use the word information, uncertainty. Um, Other definitions also use the word surprise, right? How surprising some kind of output actually is. But in general, this is not very hard to understand, right? So again, you can watch all the videos that exist about the intuition behind the entropy, but essentially is you have some probability distribution, how certainty you can be what that something is about to happen, right? If I tell you that tomorrow, the probability that tomorrow rains is zero point 0.5, that means that I don't have any idea of what's going to happen. If I tell you that the probability is zero point 0.1, that means that I have zero point 0.9 of certainty that tomorrow is going to rain. So actually the uncertainty and the information that the probability distribution carries is actually higher than the first one when I have zero point 0.5 and zero point 0.5. And that kind of explains why the for example, the problem of uh, a coin is so important in statistics because you have some event of zero point 0.5 and the other event also has zero point 0.5, which is the maximum number, the maximum amount of uncertainty. You don't know anything about that event, essentially, right? Anything can happen. But again, you can watch all those videos. I'm more interested in this part, right? So, but this is the essential idea. This is what we're trying to do, right? So essentially, when we want to build a function that, given some probability distribution, returns this number of information or certainty or um, surprise, we need to follow some ideas, right? And this is the idea that Shannon actually followed in the original paper. I'm going to follow the original derivation from Shannon in the foundational paper of information theory, right? So actually, we will follow Shannon's original ideas, right? And this is very important because there are different ways to derive this formula of Shannon entropy, right? You can see very different axioms and therefore different ways to derive that. But I'm going to follow the original derivation from Shannon, which is actually pretty interesting because there are very interesting ideas over there, right? Now, let's suppose that we don't know this, of course, because this is what we want to derive. The only thing that we know is we want to build something like this, right? We want to build a function that actually answers this. So now let's say that I'm going to write this in a new page. Now, let h is one function that I don't know, right? Be a function that measures uh, this, right? This idea. Let's suppose that that function exists, which is actually a good. This is something that you need to do some assumption that you need to put in here because we don't know if that function actually exists. That's something that we need to build, that we need to prove, right? But let's suppose that the function exists and the function is trying to solve this problem, right? So if that function existed, then that function should follow the following properties, right? Because we're trying to create something based on a probability distribution that is trying to measure something, right? So it makes sense to think that the function should follow the following properties, right? So the function h uh, basically should meet the following properties, right? And this is where things get a bit interesting, right? Because just as in mathematics, where basically you start from some set of axioms and then you derive a whole new theory from that, we are doing the same. And actually, these are the axioms of information theory, right? So, yeah, you can consider that the following things are actually axioms, and the function h should follow these things, right? This is what essentially we're trying to do. If we created a new theory from a different sets of actions, probably we will have something different. But all these things are actually treated in the Shannon, in the original Shannon paper, which I'm going to leave here in the comments. So, well, or the description of the video, something like that, right? So, anyway, so the first condition, which is actually something that is pretty intuitive, right? Small changes in P, which is the probability distribution, right, should result in small changes in HP, right? What does that mean? So essentially, you have a probability distribution, right? Uh, if that probability distribution changes just a bit, for example, if the probability of rain is 0.5, if that changes to 0.01, then the level of uncertainty that you have about that event shouldn't change radically based on that change in the probability distribution. That makes a lot of sense, right? So the amount of information that you have is actually changing in a similar way to the subjacent probability distribution that you have, right? So this actually makes a lot of sense. So in mathematical terms, there is actually a very nice way to say this, a very fancy way, actually. This means that H should be continuous, right? So H is continuous on P, right? This is one of the many definitions that continuousness has, which is actually a very small change in the independent variable actually result in small changes in the dependent variable, which is a really nice definition. Now, so this is the first thing, very intuitive, right? The second one is something like this. So let's suppose that we have this probability distribution. So we have the probability distribution P, P1, P2, Pn, and this is the maximum uncertainty that we can have for n events. All of them have the exact same probability. So any of them can happen, right? So we have P, and then we have Q, which is Q1, Q2, and this goes up to all the way to M, right? So, and then we have the same, right? So notice that H is a function that goes from the probability distribution space, which is something very high dimensional, but it returns a number, a real number, right? So it's essentially measuring the uncertainty based on some things that we will discuss, but it's returning some number, right? So technically, you can compare the entropy of P and the entropy of Q. No matter that they live in different spaces, because we have here n events and here we have m events, that doesn't matter. At the end, we can compare the entropy between those two things, right? So the question is, how can we compare both things? Now, let's suppose that plus this, we have n is actually less or equal than m, right? So what should happen is the entropy for P is actually less or equal than the entropy of M, right? And why does this make sense, right? This is not as clear as the previous one, right? But actually, if you think about this a bit, this makes a lot of sense, right? So essentially what you are saying here is if you are in the position that you have n events, all of them have the same probability. You have the maximum amount of uncertainty, Therefore, you have the minimum amount of information. If I tell you that you have n events, but all of them can happen, then you don't know anything, right? So you don't know anything about this event and you don't know anything about this event, but you have more numbers here. You have more events, sorry, in this point, right? So even though you are in the uniform distribution, at the end, since you have more possible outcomes here, then the uncertainty in this point should be higher than this, right? That's essentially why this makes sense. So this in mathematical terms means that H is a monotonic increasing function on the number of elements in the distribution. This is not completely accurate from the mathematical perspective because this is not like, sorry, this is not HM, this is H. This is not that you are comparing like the number itself. You're comparing a distribution with that number of events. But I mean, you can understand the idea here, right? So we have this axiom makes a lot of sense. And then we have the third one, which is actually pretty interesting, but here things get a bit tricky, right? Uh, And the different versions of the axioms of information theory can differ in this point, right? Because there are a lot of ways to state what we're going to state here in the point C. But again, this is the original derivation from Shannon. So this is how the concept was introduced. Now, let's suppose the following. Now, let X, this space, right, which n different events, be a set of events and pi is the probability that each of these events happen, right? Now, let let's define the following. Now, let C1, C2, Cn, well, actually, this is Cm, right? It can have an arbitrary number, right? Be a disjoint set of subsets of X. That is, each of these is actually a subset of this space here, right? And X is the union of all of these subsets. In mathematics, this means that C1, C2, Cm is a partition of X, right? So basically, we have a partition. You take different subsets of the original set, and then the union of the disjoint union of all of those sets is actually the original one. That's a partition, right? And you can understand why that's called the partition. Um, let me write something here. Let me do this diagram. So let's suppose we have something like this, right? You have the original distribution, and then you have a lot of subsets like this, like this, like this, right? This is the partition that we have now. So this is X, and each of these things, so this is X, and each of these things that I'm sketching here are the events of the original space. For example, this is X1, this is X2, this is X3, and so on, right? The red ones are the original events here in the space, right? Now, what we're telling is that we are dividing this space in C subsets. So for example, this one is, let's write this is C1, right? This other element over here, let me write it here. For example, this one is C2, and so on, right? So essentially, the C subsets contain different elements of the original space, right? Different events of the original space, right? This is essentially what we have here. Now, now, so so what the property says, right? The axiom says here is essentially you have your original space and you're creating a new one with these divisions, right? Technically, you can compute the probability of each of these events, but now being aware of the new partition of the set of the probability space, right? So the question is, how does it relate the probability of this and the probability of this, given that you are partitioning your original space, right? So notice that the probability of one event, for example, the event xi, right? Let's say this is xi. Well, for example, let's this nice color here, right? So the probability of xi, so this is xi and this is ci, right? xi is contained in ci, right? So you can compute the probability following the properties of probability, right? So the probability of xi is the probability of ci, right? Is the probability of the big space that you have here, right? Multiplied by the probability of xi inside this new group, right? You are basically selecting the big element that contains xi. That's the first choice that you need to do. And then after that, you are choosing xi considering that you are inside the new group, right? That's a probability. That's a conditional probability, right? So the probability of xi is the probability of ci multiplied by the probability that you choose xi given that you are already in ci, right? Um, this is pretty simple. This is actually, the definition of, you can derive this from the definition of conditional probability, right? This is um, pretty simple to prove. Actually, if you follow the definition of conditional probability, this is actually, uh, so this is the probability of xi intersected with this, divided the probability of ci, right? And then this, since xi is contained in ci, this is exactly xi. So basically, this is pretty simple to prove. That's something that you can see. But this is not the important part. This is just, I'm just showing you how this is computed, right? Just to have a sense about the formula that I'm about to write, because this is kind of, um, because this is kind of, you know, confusing at first, right? So you have this setup, and what the axiom says is, how can we compute the entropy based on everything that we have written here, right? So then the entropy of P1, P2, Pn, meaning that you are computing the probability of the original events, right, relates to the probability of, to the entropy, sorry, of the big events like this in the following way, right? So I think I didn't write that. Now, let Qi be the probability of these spaces, right? Of these events, right? So this is also a notation that we will follow, right? So if we want to compute this entropy, so this is the entropy of Q1 Qm, meaning that you are first computing the entropy of the bigger group, right? Plus this term, which is actually pretty interesting, then you are going over all the different groups that you have here, C1, C2, Cm, and then you are computing the entropy for each of the elements given that you are inside Ci, right? So Qi, right? Multiplied by the entropy of this thing that I'm going to write here, which is essentially, this can be a bit confusing. I understand notation sometimes it's not the best, but this is exactly what I just told you. So here you are computing the entropy across over all the different groups, and then this is essentially the entropy just restricted in each of these groups. So for example, here you are already inside this group, inside this subset, and then you are computing the entropy for each of these points given that you are already inside Ci, right? Which is ex exactly what this means. Notice that this is actually a new probability distribution, right? And this is the probability distribution of xj given that you are already in Ci, right? Uh, and that's why I just wanted you to understand this, because if you see, this is exactly the same idea that we have here, right? You have the uncertainty, the entropy, the information that you have in Ci, and then you have the information for each of the subsets of the set Ci, right? But again, um, this is an axiom of the information theory, and what this says is that H should be consistent across the different ways of computing the original probability, right? Right? So this is, I mean, in other words, right? No matter how you compute the entropy, right? No matter how you compute this H, that information, you should get the same result, right? You should, at the end, have the same amount of information. Changing the way how you compute that shouldn't change the final number that you should get. Um, so this is kind of interesting. As I told you, there are different ways to define this. So in different approaches, you will find, for example, the additivity property, which says that H should actually be an additive function, meaning that the H of the sum is actually the sum of H, which something like that. That's a different way to define this, but this is the minimal amount of axioms that you actually need to derive our original formula of Shannon entropy, which is actually, again, what we are trying to do here. I was just trying to give you some sense about how these axioms actually work and what they are important and why they make sense if you think a bit about it, right? So this is essentially what we have. Okay, now, given that we have already discussed about all the axioms, now let's start with the derivation, with the actual derivation of the formula, which actually has three different steps, right? So the claim, so we are claiming that there is one function that basically follows the three different axioms that we have there, and that function is actually unique, right? So the claim here is that if P is a probability distribution, right, meaning that the sum of all of this is one, right, then HP defined this way is the only function that satisfies A, B, C, right? And how are we going to prove that? So essentially, we're going to build this function. If you have a set of properties, right, and you start deriving the formula of that function that actually follows the set of properties that you have, then technically you have shown that if one function follows the same set of properties, then that function should be the same than the one that you build because you're directly building the function. So our approach here is we're going to build the function in three different steps, right? So we will break. So let's put this line here because this is what we are going to prove, right? So essentially, we will break this. We will break this in three different parts, right? This is the kind of proofs that are really interesting because they are very, you are building an object in sequential steps. I really love this kind of things, right? So we're going to build this in three different parts. The first part, um, we will show, so basically we want to show that this thing, let's put this here. So this thing, so we will show that this holds for P equal 1 over n, 1 over n times, right? So the first thing is showing that if you have the uniform probability distribution, right, then this is actually true, right? Notice that this is a very specific case. This is very general because here you have any kind of numbers that form a probability distribution. Here I only have this very specific probability distribution, but this is the first step. If we show this, then we are on a good track, right? So this is the first thing. The second thing that we want to follow is that the same thing holds if all pi are rational numbers, right? And of course, rational numbers in zero in the in 0.1, right? So in 0.1, right? Not 0.1, but 0.1, right? So this is the second thing. Again, this is a more general case than this, but this is still very, very, very specific, right? Not all the probability distributions have to be rational. You can have some very weird probability distribution that some event has an irrational probability. Just think about, I don't know, some kind of probability that has involved the p-value, the p number, right? P that 3.14, 15, whatever, right? That's not rational, right? And you can have probability distributions that have that shape, right? So this is still very general, but we are slowly creating all the things that we need to build the function in the general case. And actually, these two are the hardest ones, right? The third part is actually showing this for all the elements, right? So The third part is uh, that show that this thing here holds for all pi in R. Well, not pi, basically. Yeah, let's suppose these are real number. Of course, they need to sum up to one. But anyway, let's put this in this way. So here we are proving this for all the real numbers. So these are not rational anymore. This can be irrational numbers, but this is actually a pretty natural sequence of proofs. Um, and at the end, you will see that this is the easiest one. Right? Now, this is the sketch of our proof, and I want to tell you again one of the things that are very interesting to me, right? One of the things that has always amazed me. This is actually a proof, right? This is actually something that you can prove. This is not just a definition, right? It's not that Shannon decided that this is a good function for this. You start from some set of axioms, and then you derive the formula that you use in your daily basis, right? This is the formula that you use for cross entropy when you are training a binary classification model, a multi-class classification model, or something like that. Which is not the only loss function, but it's pretty common, right? So this is actually pretty interesting. Now, let's start then with the point one, right? With this point. So let's again put this line here and let's start with one, right? Now, what are we gonna do? So let's start defining this new function. Well, this notation, not a function, but this notation. So let's define an as h1n and so on, right? So essentially, we are just giving a name for this value that we have here, right? So an is just the Shannon entropy, or well, the entropy of these elements that we have here, right? Now, let's take two different numbers, right? So let S R two natural numbers, right? Be fixed natural numbers, right? Um, right? And let's pick one n natural, another natural number, right? And essentially what we want to show is that given this natural number, we have a different natural number for which one relationship that we want to prove always exists. These kind of arguments are pretty common in mathematics. You pick one n and then you show that different element exists that make your that make what you want to prove to hold, right? In that case, then you can prove the differences that you want to prove. But you will understand that better, right? This is just a formality, to be honest. This is just trying to be a formal. I just wanted to be a good mathematician, even though I am not. So yeah, so essentially we have here, and notice that if we compute this quantity, right, Sn, right, which is Sn is a natural number again, right? This is H 1 over Sn, 1 over Sn. And this actually repeats for Sn elements, right? Again, this is just a natural number, so you don't need to worry about this. This can be extremely high, this can be extremely small, that doesn't matter. The only important part is that this is actually a natural number, right? So, notice that interesting part here, right? If we have a subset, if we have, now let's suppose we have a new space of Sn elements, right? s to the power n elements, right? You have a new probability space. For example, this let's say you have this one. Let's write this in this way, and you have a lot of very small subsets like this, 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 right? And you have Sn elements in total, right? Uh, Notice that something that you can do here is you can divide this space with this quantity in S groups of size Sn minus 1, right? So, for example, you have here, so you can divide this in, let's suppose this here is Sn minus 1, then you can do this. Now let's write this in a different way. So you can do this. This is S n minus 1 and so on. And you can create S groups of S n minus 1. Why is that true? Because essentially you have S to the n. If you have S groups of size Sn minus 1, then at the end, if you sum all of them, you are going to have Sn, right? So what I'm trying to say is Sn is S minus 1, right? So you can divide, so we can divide Sn groups in S groups of size S and minus 1, right? This is something that we can do. And all of those numbers, all of those events, sorry, because here I'm talking about the number of events, but at the end, what we are trying to do is just divide in some big probability space, right? All of those small spaces actually have probability 1 over s, right? Because we are dividing this space in uniform events, right? So let me write this here more specifically. So we can divide the space with Sn, let's say it with Sn uniform events. That's why we are computing this, right? In S groups, each of them with size is n minus 1, right? Why we're trying to do this? I know this seems a bit artificial, right? And it is. I'm not going to tell you that this is not artificial, but what we're trying to do is actually following this idea, right? Notice that essentially we are building everything so we can apply this here now. So given that we are doing exactly what the third property says, then we can apply that property, right? So we can apply um, C, right? Let's put this in a different color. We can apply C to obtain H1Sn, 1Sn, right? This is H1 over S, 1 over S. Why S? Because you're dividing this in S groups, which is exactly what we have here. And the probability of each of those groups is actually 1 over S, because each of these small groups have probability 1 over Sn. So at the end, if you have these big groups, you have S groups of probability of equal probability. So each of those groups actually has this probability, right? So let me write this small number. So this is H1 over Sn. S, and this is H 1 over S 1 over S plus, if we follow that, right, remember that here we have here, which is essentially the probability of the new groups. The probability of this group multiplied by H in that new probability, in that new probability space of the conditional probability, right? So this is the sum of I going from 1 to S. Why to S? Because you have S different groups again, right? Then the probability of each of those groups, the probability of going to each of the new subsets, which is basically 1 over S, right? I'm going to write this even smaller so I have space. 1 over S, H, what's the probability of one of these individual events that we have here? That probability is 1 over S to the n minus 1, right? Why? Because if you have here, right, let's let's focus on this group, right? If this group here has S to the n minus 1 elements, then what's the probability of each of these elements, given that you're already here, right? Then the probability of 1 is 1 over S to the n minus 1, right? Because this is the conditional probability of each of these elements, given that you are already here, right? So this is 1 over S minus 1, 1 over S minus 1, right? That's great. Now let's translate this in different terms, right? What we have here. So what we have here is A to the S, A of S to the n, right? This is A, sorry, this is A of S. This is 1 over S, which is actually constant because this doesn't depend on I. So I can move that outside. But this thing inside is actually A to the S minus 1, right? So if I write this in a different way, we are telling that this is A of S to the n equal to A of S plus 1 over S. I can move this outside that sum. I from 1 to S, and this is A to S and minus 1, right? Notice that this doesn't depend on I, right? So this is actually a constant term that you are summing a lot of times, right? So this is A to the S plus 1 to the S. I can move this outside, right? And then we have the sum of A1 to S. What's inside is essentially 1, right? You are moving everything outside the sum. And this is pretty simple. This is just S. So I have A to A of S plus 1S, AS minus 1. And this thing inside is S, but notice that this S here and this S here cancels out. So we have A of S plus A of S and minus 1. So this is, you might be wondering, why are we doing this, right? And yeah, I know this is kind of tricky. Again, I'm just trying to follow the original proof from Shannon. Of course, figuring out this is actually pretty hard, and that's why Shannon is famous for all this work, right? Because he basically saw that doing all these things are going to give you the final result. Um, but again, this is just trying to follow it. Now, this is actually pretty interesting. Notice that what we have here is a very interesting recursive expression because between A. So you can plug this in here again, and then again, and this is actually recursive. And you can see, right? So we can easily see that this means that a of s to the n is actually to n a to the s, right? So why is that? Because again, you can plug this in here and then repeating that. And then, for example, if I repeat this for this, then we are going to have a of s two times and then plus a to the s n minus 2. And if you go to the end, then you will see that you have a s several times and the number of times is actually n, right? So this is actually pretty interesting, right? This is showing you that the function a that we just defined has this really nice property, right? Of taking the exponent and then multiplying with the a function without the s, without the exponent, right? If you remember, this is actually one of the properties of logarithm. So we are starting to see something interesting. Now, here's the point, right? So we have s to the n, right? But remember that we defined at the very beginning not only s, we also defined this number r, right? And we defined that for some reason, right? Here's the tricky part, right? We have s to the n, which is a natural number, right? We have r, which is a fixed natural number, right? So let me write that. So remember, r is a fixed natural number. Here's the point, right? We can find a new number n. This number actually depends on r, on n, such that r to the m is less or equal to s to the n, and this is less or equal to this. Why is that true? And actually, this seems fancier than it is, actually. This is actually a pretty simple result, and this is because you can write all the natural numbers as the union of these, right? What this means is, for example, I mean, in simpler terms, for example, if r is equal to 2, then you can write the natural numbers of, um, so actually this starts from 0, right? So for example, 2 to the 0, 2 to the 1, union 2 to the 1, 2 to the 2, union 2 to the 2, 2 to the 3, and so on, right? So essentially what you are doing is just, you have here the natural number lines, and you are creating these sets that are actually bigger and bigger, but essentially um, you're just getting every single number in one of these subsets, right? So this is just to give you one sense of why this is true. This is not really important. The important part is that this is actually true, right? But if you understand this, I mean, it's pretty interesting, right? This is, oh, sorry. Uh, just, I just wanted you to understand this. This is not relevant for our conversation. I just wanted to convince you that this is not some very dark magic or something like that. Oh, let's put this right now. But this is the point, right? We have defined, not defined, we have found some element like this, and this number is actually unique, right? Because we already have defined r, s, and n, right? Now, notice that we have here, and these guys here are actually natural numbers, right? R is natural number, S natural number, N is natural number, M is natural number, right? Um, so, right, we have here, given this, right? So, following this, we know something about this, right? Because the first condition, the second condition, sorry, is actually telling us something about this, right? This is actually a relationship between H, and we defined A as exactly these values, right? When we have a distribution that is actually following this, right? So we can apply that for A, right? So we have that A to the M is less or equal that A to the Sn, and this is less or equal that R to the M plus 1, right? We are just applying A um, to all the sides of this inequality that we have here, right? But we know something about A. We have proved this, right? So we know that this is M A over R less or equal to N to S. This is M plus 1, right? Now, something that we can do here is just, we can divide this by, um, so we can divide, I'm gonna put this in blue. So we can divide all the sides, by this value in um, A of R, right? Right? So essentially what we want to do is just um, taking these values here that are outside my inequality and just put them in here, right? So I'm just dividing this by M A R divided N A R. This is less or equal AS divided N A R. This is M plus 1 divided N A R A of R, sorry, right? Of course, this cancels out, so we have that A of S divided A of R is less or equal than these two quantities. And notice that this is M divided N plus 1 over N. If I subtract this element from all the sides of the inequality, then this is 0 less or equal to S A R minus Mn. This is less or equal to N. And I can apply absolute value because these numbers are positive for this side of the inequality. So this is the same than A of S divided A of R minus M of N. This is less. Actually, this is less, right? This is not less or equal here. This is strictly less. This is important, okay, than M over N. Why is that important? Actually, this seems pretty artificial. This seems pretty magic, right? But this is actually pretty important, right? This is one of the things that we want to prove, right? Um, we cannot do something directly from this because at the end, this also depends on N. This is not that I can just make this thing tend to infinity because we cannot do that from now because this also depends on N. But this is one very important part of the inequality, right? Just let's keep this for a moment and then let's go back to this thing that we have here, right? right? Notice that, and I'm gonna highlight this because this is very important, right? Notice that from this inequality, we can apply log to all the sides. Was that true? Because this is our natural numbers, right? Log is an increasing function. So if I have a inequality that looks like this, basically we can apply that to all the sides of the inequality. So let's, so from T, let's take log to both sides, right? So we have log of Rm, this is less or equal of log Sn, less or equal of log the Rm plus 1, right? We can apply properties of log. So we know that log actually follows this. This is n as n plus 1 log of r, right? And again, we can do something similar. We can divide this by n of log r, right? Log of r, right? So we can divide this again. Um, so dividing by n log r, right? Which we can do that because this is non-zero because r is a positive number, a natural number, and uh, bigger than 1, right? If r is 1, then this is trivial, so we can assume that. Uh, so we have m divided n log r and n log s divided log r m plus 1 divided n log r log r. So this is m divided 1, m divided n log s log r m plus 1 and log, sorry, this cancels out again. We can do the same thing that we did, so we can show that this is exactly to this, right? And again, this is not less or equal. This is a strict, right? This is important, right? And this is the second part of this. Probably you can imagine what's going next, right? So we have this, right? We have this, and we have this. So we can compute the following. Notice that a of s, a of r, minus log of s, log of r. Yeah, exactly. What we are trying to show is that actually this and this is equal to this. This is exactly what we're trying to do here, right? So this is something very cool that we can do is notice that as 8r minus mn plus, um, let me write this here, right? So this is, yeah, let's write this as negative, right? This is log s log r minus mn, right? You can see that this is actually true because this minus is actually changes this, which is the original thing that we had here. And this minus is positive, so these two things cancels out and I'm not doing anything wrong here, right? So this is the same to as, let me write this again, right? Just to convince you that this is actually true, right? Sorry. So this is negative here. Minus m and 2, right? Um, no, but I think there's something better I can do, probably this is not, yeah, I mean, uh, yeah, it's kind of ugly what I'm gonna do next, but it's possible, right? And probably this is just doing very unnecessary things, but doesn't matter, right? Just I want to be as um, yeah, I mean, as strict as possible, right? Notice that what I just wrote here is exactly what we had at the beginning. This is just one way to write this, right? So, but this is absolute value, right? So this is the absolute value of two quantities, of this number and this number. So we can apply the triangle inequality, right? So this is a s a r minus m over n plus the absolute value of this quantity that we have here, that negative, right? Log s log r. This is very detailed, by the way. I'm just writing as much details as possible, right? So we applied here just the triangle inequality, right? And the absolute value has this nice property that the absolute value of a negative number is actually the absolute value of the positive one. So this is a s a r minus plus log s divided log r minus mn, right? So this is actually the same, just I'm here and just applying that the absolute value of a is the absolute value of minus, right? Now, here's the point. Notice that we already have an inequality for this and also an inequality for this, which is this and this. So this is less than 1 over n plus 1 over n, and this is for this and this, right? So this is 2n. Let me write again what we have. Noticed that we have a very long sequence of things. So so that means that notice that the first inequality that the first term that we had was this, right? So we have a s a r minus log s log r. This is less, strictly less, right? Because all of these terms were equal. We have this inequality and then we have this inequality. So we are doing, so we are following the proper steps. This is 2, right? And here's the point. Notice that all the sequence of things that we have proved show that for each n, notice that we took n as any natural number, so n can be big, n can be small, it doesn't matter. We are following a very strong line of uh, arguments that actually show that for all natural numbers, right? So that means that for any natural number n, we have this thing. And if you have this for any natural number, that means that you have here for numbers as big as possible. So that should be that this is actually 0. So that means that this guy here log r is actually 0. And if that's 0, that means that as ar should be exactly equal to this. If that's true, that the division of these values is the division of this, that means that a to the x, let's say a to the n, just new natural number, it's one constant and the logarithm of that n. Why that constant? Because notice that basically for each constant, uh, you are following this equality that you have here, right? Because the constant basically cancels out and you have the same. So being completely strict, that means that we have here, right? So, right. So we have proved, sorry. So we have proved that a to the n, which is h1 over n, is basically one constant on the logarithm of n. That constant is actually not very big because at the end, that constant, what it's doing is just changing the scale of the value of the number. So we can define, so let's take just one. I mean, without lose any generality, because again, that case just changing the scale of the value, right? So you can do that, and at the end, you are not changing the distribution of anything. So a to the n, h to the 1n, 1n is the log of n, right? Uh, that's it, right? That's it. Um, right, because at the end, we said that this actually holds for this, but notice that this expression is, let me write this again. So this expression, we can write this as 1n, 1n log of 1n, right? The log of n, sorry, right? Um, log of, sorry, again. So this here, this thing here is the same than um, minus 1 over n. Sorry, yeah, I was writing that correct. 1 over n, right? And why is that true? Because this is completely constant. So 1 over n, this goes outside the sum. Then we have n, and then by properties of logarithm, we can move this. I mean, this thing here is, sorry, sorry. This thing here is n to the minus 1. So at the end, we can apply the properties of logarithm. And these two things are exactly the same thing. And this is applying our probability distribution to the initial uh, function that we have. So actually, this proves the first part, right? This proves the point 1. And this shows that when you have uniform, of course, all of this is for discrete probabilities. We have the formula of the Shannon entropy. So that's the first part. So let's move on to the second part of the proof, right? So we have proved this for natural numbers, let's say, just for distributions that look like this. Now let's move to this second part, right? So let's try to prove this for rational numbers. As you will see, um, the first part is actually the the more complex one. The second is kind of easier, right? And the third part is actually the easiest one. So this is actually getting easier on the as long as we go to the end, right? So again, let me create this line here. Now, um, let's prove that this actually holds if we have rational numbers, right? Now, let's assume, oh, yeah. So now, let's assume that this guy here, this probability distribution P1, P2, and so on, has rational entries, right? So that means that all the numbers p1, p2 up to pn can be written as some kind of rational number with a numerator and a denominator. Something that we can see very easily is that we can write each of these pi as this, right? So one natural number in the numerator, right? And some t in the denominator. That t is fixed, right? So where again, air I is a natural number and t is a natural number. And why is that true? Well, because you have a finite number of rational numbers, so you can, for example, compute the sum of the denominators and I mean um, and then you can prove that this t actually exists. You can build that very easily just computing the sum between all the p's, and you can have like the a constant t in the denominator, right? So this is something that we can write um, very easy, right? So at the end then we have p air 1 t air 2 t and so on, right? And these new air numbers actually uh, shows you can see that then we have this and air 1 plus air 2 plus air n is equal to t. And why is that? Because this is a probability distribution, right? So actually you have initially that the sum of all the p1, p2 up to pn is 1. And since you are writing this in this way, then essentially this should follow, right? Okay, so we are just writing this in a different way. Now let's do the following. So notice that t is a natural number, right? So we can build something like the following probability space, right? Now let's take the space with t events, each of them with probability 1 over t. That's something we can do, right? Just t events, all of them with the same probability, right? So we have something like this. So uh, kind of a Turing event with all the events with the same probabilities, right? So for example, this one has probability 1 over t, and we have t events. Let me move this to the left. Okay. Now, notice that we can do something. Air I is also a natural number, right? So it's the size of something, the size of some set, right? So we can divide this space in C1, C2, Cn subsets with size air I, right? Notice that what we are doing here is just taking this space and dividing it in sorry, that was unnecessary big. This subsets like this, right? And this subset has air I elements, right? And we are dividing our space this way, right? This is something pretty natural that we can do, right? Now, here's the very interesting part. Notice that the probability of each of these spaces, right? So what's the probability of that? What's the probability of getting to this group, right? we have t elements with the same probability, right? So if we are subdividing this space with I elements of size of probability 1 over t, then the probability of this is just the number of elements that belong to that subset divided by the total number t that we have here, which is exactly pi, right? Our probability distribution. Why? Well, you have a lot of subsets with the same probability, then you're grouping them in a group of size Ri, so the probability of that new group is just something like this, right? This is extremely important, right? Because we can apply the third axiom, right? We had an original probability space, we divided that way, so we can write this in two different ways. So by 3, right, by C, we have that h of 1t, right, which is 1t, right, is the same of h of this new probability distribution of getting to the B group, P1, P1, Pn, plus the sum of going from 1 to n, P1. And now here comes the question. What's the probability distribution of the conditional probability here? Right. Well, you are already in this group, which contains Ri elements, right? So each of those groups, each of those elements has the same probability, right? Since you have Ri elements, each of these elements in the conditional space has probability 1 over Ri, right? Because you have Ri elements, each of them with the same probability, then that conditional probability is just 1 over Ri, right? And by the previous point, we already know what is this, right? We know that this is log t, right? So this is h b1 bn plus the sum of 1 over n br h. Notice that, I mean, we can write this in different way, but just write this for now because this is a Ri. But let me write this in this new space. Notice that this guy here, right? We know that 1 h 1 over Ri and so on. This is a Ri or this is log Ri, right? By the previous point, right? So let's do some algebra here. This is log t h b1 bn plus 1n bi log Ri. Okay, but remember that Ri, we can write that following this, right? Ri is just pi multiplied by t, right? So this is log t h p1 pn plus p1 and pi log of Ri, sorry, pi t, right? So okay, let's do this. Log t h p1 pn plus pi by properties of the logarithm. This is pi plus log t, right? So let's see. This is, I'm just following this. H p1 pn. So I'm gonna write this. Hopefully you don't get lost by this. This is E1 EI log EI plus log t e1 and pi, right? I just divided this sum and I moved this out of the sum, right? And here's the very interesting part. This guy here is 1. Why? Because this is a probability distribution, right? So notice that we have this really nice thing, E1, Pn plus E1 and Pi log Pi plus log T, right? This log T is here because I was summing this here. And this log T is present in both sides of the equality. So this cancels out this. So on the left, we have 0 equal to h of P1 Pn plus P1 and Pi log Pi. And of course, moving this to the left, we have this really nice result, right? Which is exactly what we wanted to prove, right? Which is the formula of the Shannon entropy for rational numbers, right? Notice that this is extremely elegant, right? These are just very smart, very clever ideas about how to play around with these new probabilities spaces, doing that in a very clever way so we can get to this result. Now, this holds for rational number. We haven't finished yet, but we are extremely close. Actually, we did the most important part of the proof. So we have already shown this, and then let's go to the last part of this, right? So um, let's go to the three, the third part of the proof, which is uh, real numbers, right? So let P, P1, Pn be a probability distribution. Again, this is a probability distribution, but where Pi are real numbers. That means they are not necessarily rational. So this argument here actually doesn't work in this case because for irrational numbers, for example, you cannot do this, right? But there is a very interesting argument, which is actually the key point here. This is trivial when you have the result, right? So this is very well known in analysis, mathematical analysis, right? For each real number, right, there exists a sequence, let's say a sequence Qi of rational numbers such that the limit of this sequence is exactly the real number that you have. This is a very interesting result in analysis. Of course, I'm not going to dig deeper in this. If you are interested in this kind of results, I really encourage you to read a bit about real analysis and this kind of results. This is actually pretty interesting. And that's it, right? I mean, this result actually gives you pretty much everything you need, right? Because basically for each of the elements in this distribution, we can get, so of course there are some details. This is not completely formal, but this is the main idea. So let this be a sequence that basically this for each element converges to this uh, if j goes to infinity, right? So for each j, right, you have that h, kj1, kj2, right, kjn is minus. Yeah, I'm just writing this for each of the elements of the sequence, right? And of course, this thing about the indexes is kind of annoying, but uh, so let's see this. So okay, so for each j, which is the element of the sequence, okay, we have this. So the index is definitely here because uh, each of these elements are the ones that converge to each of these. So that's fine, right? But of course, notice that until this point, we hadn't used the first condition, right? The first axiom that we defined about the continuity of this guy, right? Uh, Everything that we did in point 1 and 2 basically didn't use the that condition, but here we are using that, right? Um, because we have this for each of the elements in the sequence, right? But for A, one of the conditions of the if a function is continuous, one of the great things about that is the limit of the function applied to some sequence is actually the limit, is the function applied to the limit of that sequence, right? So we have this, right, for each of the elements that this actually converges to these numbers, right? Because h is continuous, right? Continuous, right? Each is continuous, and for each of these values, we have a sequence of rational numbers, so we can apply the result that we derived in 2, right? And that's it, right? That's it, because this is this, and this is actually the limit of that, right? So in the limit, we have that actually this actually holds. Of course, again, uh, if you are a mathematician and you are seeing this, of course, I missed a lot of details in this specific part because this is very this has a flavor of analysis, right? And there are a lot of details. But the only thing that you need to know is for each element in the original probability distribution, you have a sequence of rational numbers that allows you to apply this, which is for 2, right? This allows you to apply this, and then since h is continuous, then in the limit, this should converge to this. So again, since this is continuous, the limit of this is actually this applied to the number, right? Applied to the probability distribution, right? If h weren't continuous, this might not be the case, but since h is continuous, that's why this is a very important axiom. And that's it, right? We have proven this for rational numbers, and we have proven this for real numbers. So that means, so for 3, we have proved our result. So just a few comments about this. Notice that from the point 1, remember the constant. So technically, the Shannon entropy definition, or the Shannon entropy expression, let's say, can have one constant, right? That constant, I mean, is it's not relevant in the sense that if you have that value multiplied by 2 by 3, that's only scaling the value of entropy, right? Uh, so that's it. Yeah, that's what I wanted to show you. It's really interesting how this is not a definition, right? The definition is about uh, the axioms of information theory, right? But the result of Shannon entropy is actually something that requires some proof. And that's why I wanted to show you that.